Okay, we start up. Any questions before we begin? Everything is A-OK? We like it. You have now been given the third report exercise. We have to keep up the pace here. Time is running. It's almost Christmas. And here I have now created the group for the third report for exercise 6. Hopefully then nobody has been a member of another, well, you should all be unfamiliar with each other. I want to go through a little bit of the exercise. Let's have a look. So here we have exercise 6. And yes, it's a free surface problem. And yes, it is three-dimensional, it is transient, and it is turbulent. So thank you very much. We are only missing chemical reactions here to have a really nasty case. But try to keep the resolutions low. Just to give you an idea what you should obtain here. See if I can make it work this time. So you have the layout looking something like this. So you have a small little block inside a huge, say, aquarium. And we are then going to make a contour of alpha, and we make the contour 0.5. Remember, alpha, that was the parameter who distinguished between water and air, of the two fluids that you are using. So there you have the setup geometry. So you have a lump of water contained in the right part of this aquarium tank, and then at time equals 0 you release it, and then the water should flow and then hit this tiny little box, and then you have a lot of sloshing. For this problem, we have been given experimental data. Actually, on the top of this cute little box here, they have put in the experiment 8 pressure sensors. So we have the pressure values as a function of time on this little box. So when you run, of course, initially, you might think, it's no water hitting it, then the pressure should be constant before the water slams into it. No. Why is that? Well, that is because you have also the air flowing here. Let's see now if we show, well, I can't use the same slice, can I? No, that won't work. But the air is also moving, so it's not only the water lying in the bottom of the tank, of course, the air is also moving here, and then hence also produce a pressure. Not big, but it's going to be there. So yeah, you have some small values, but then when the water hits, of course, you have a density difference of 1,000, so then that's completely different pressure. But we have all measurements, and if you simulate, say, a long time, first of all, let's say now after 2 seconds, roughly, then we are somewhere here. Then you see the entire box is totally covered with water. So all 8 pressure sensors should now, say, measure the pressure also from not only the air, but from the water also, after 2 seconds. The data that we have received from the experiments, I think they last 8 seconds. So, of course, in the end simulation that you are going to do for this exercise, yeah, you should simulate actually all the way to the to 8 seconds. But I mean, initially you will sort of start with only the first couple of seconds. Here actually the top is clear again, and then it's covered with water again. It's a heavy simulation, of course, so I hope you have plenty of CPUs on your little laptops. So this is what you should sort of obtain in the end. How to do it? Well, first of all, what's important for this exercise then? Of course, the meshing. That will be task 1. Get in this geometry. I've put up 3 options for you. You can use a snappy hex mesh around a solid box. And I have given you an STL file with such a box. Should be the correct dimension and the correct position. So you can use that one and just use snappy hex mesh around this box. That should work. Or you can use snappy hex mesh but not use a STL file, an object. You can create simple geometries inside snappy hex mesh without an STL file. That's actually a possibility. Let me show you. Where are we? Here. Gedit, system, snappy. So this would be one way to do it. Use an STL file. Another way would use what they call a refinement box or a searchable box. You can give him any name you like, just a box. But a searchable box where you give the position for the diagonal, the lowest XYZ positions and the maximum XYZ positions. That would be another option, and still use snappy hex mesh, possible. A little bit messy maybe, but it's possible to make it work. And then the third option, if you look at the geometry, yeah, you can create this geometry in block mesh without using snappy hex mesh at all. You're going to need several blocks then. How many do you need? Well, at least 1, 2, 3, 4, 5, 6, 7, 8. And then you need the same amount at the top, 16, and then 1 over this one, 17 different blocks or something like that, to get all the geometry within the simple block mesh dictate. That's also an option for you if you prefer that one. Snappy hex mesh can be a little messy, of course. So yeah, first task, get the geometry in. And then simulate using the interphone, which is a WOF method, where we use this alpha water to differ between here, air, and water. So definitely use the 2-dimensional dam break case as a start tutorial and see how it's done. So that one is important. You're supposed to verify the results. So Courant number, essential, especially here, because we are definitely looking at the time history here. So you have to make sure that your time history is correct. I think in the dam break case they have used first order forward Euler scheme. Maybe that's not good enough. Maybe you should have a second order time scheme there, Crank-Nicholson or something like that. And also keep the Courant number low. For implicit schemes, yeah, you can have a Courant number of 2, 3, 4, 5. Don't do it. It should be 1 or smaller, clearly. And then, yes, you have to check the residuals. Remember, here you have to solve the equation system for every single time step. So make sure that the residuals at all time steps is reasonably low. And yes, you have to do a GCI study, meaning you have to do this with 3 different measures, finding the apparent order and make a result. When you compare with the experimental data, I want your results, the pressure at the different probe locations, with an error bar, with a plus minus. That's the whole point with the GCI. Then you can simulate, get a result, and you can also say something about the uncertainty of your simulated results. And then hopefully the experimental data should be within your range of your plus minus. Then you can open the champagne. You have been given here some additional files. Let's have a look at them. The setup case should be here somewhere. So there you see the little block and the water, the water block. In the experiments, I think they have done sort of a wall here, and at time equals 0, they use a weight and then they suddenly lift the wall. Of course, we will just say we have a water there, and at time equals 0, it's released. I think in the experiments, actually, you must then have some velocity going upwards here. So it's a little uncertainty there, but shouldn't be that big. Anyhow, for this little box to be hit by the water, you see the locations of the 8 different pressure sensors where we have experimental values. And you have some images from the experiments and some results here. They have actually simulated this with a Fortran program, I think, and you see they have some not perfect match. Not strangely, maybe. Initially, they follow quite nicely, but then as time goes, the difference is going to get bigger and bigger. I mean, you're using thousands of time steps, and if the error sort of accumulates up, then the error is going to be bigger and bigger, of course. So, but that's your problem. It should be within decent range. I mean, they are obviously in family, these 2 curves, but they are not perfect. You better make it better. Let's see, here you have the pressure, and here you have the entire geometry. So use this one when you construct the mesh. You know exactly where everything is from above and from the side. And here is an important thing. When you do the GCI, you have to do this with 3 different meshes. And initially, when you are using, say, interfoam, you sort of set up this region filled with water. The volume of this region should be the same in all 3 meshes. Because when you're using the script set fields, he's the one that puts initially 1 for water and 0 for air. He can only do it with 1 and zeros. You don't have anything in between. Meaning, if this volume doesn't match your mesh, then you're going to have different volumes for the 3 different meshes. That's not good. Especially for the height here. If you are, say, have a very coarse mesh, so he will have the height up here or down here, of course you'll have a totally different result. That's not good. So try to make sure when you create 3 different meshes that this initial volume is roughly the same. That's a good point, actually. For the, what's it called? I think it's the Y direction here. Of course, it goes from wall to wall, so that's not a problem. But this distance should hit a cell face somewhere here. And also the height in the Z direction here should hit a cell face close to this value, 0.55 here. And I think this one was 1.992 meters or something like that from the left side. Okay. Here you have the location of the different pressure sensors. So they should be exactly in the center of this box. And then the face towards the water here, 1, 2, 3, 4. And then you have 5, 6, 7, 8 on the top. And yeah, they have some information here about how they have simulated it. Don't pay any attention to that one. The Fortran program, so we don't care about that. But you have all you need with the geometry. Here they only give up the physical properties for water. I mean, we need it for the air as well. But I've given that one in the text, so you should have everything you need. Let's have a look. Yeah, the transport properties, I think I put it here. So here you have the constants that you are going to need for water and air, and also the surface tension, 0.07 for the surface between water and air. You have a website for this test. So you can have a look at that one if you want. You can download all the same files that I have given you. And also here we have a file called experimental data. That one should be here as well. Here we go. So here you see you have the time and then you have the different pressure for all the 8 different sensors. And as I said, initially, the water hasn't hit the box yet. So if you look at the numbers here, well, they're actually quite small. And also, they are negative. Hello, negative pressure, come on. It doesn't exist, does it? But it's an incompressible simulation. Both water and air here, they are incompressible. We don't calculate the temperature. So we just use a reference pressure, 0 somewhere, typically on the surface, on the opening of the tank. Hence, yeah, you're going to get some negative values here. So what? It doesn't really matter what reference pressure we are using. But if you go further down in this file, all of a sudden you are getting quite big numbers. Then the water has hit. So, and as I said, after 2 seconds, something like that, where are we? 1, here we are, 2 seconds. Then you see all 8 probe locations have quite high numbers, meaning they are all covered with water. So I think after 2 seconds, that should be a good monitor when you're doing the GCI. Okay, and then you have been given what else? Yeah, that's the point. As I said, the initial start volume should be the same for all meshes you are playing with. And you can actually calculate what is the water volume. And I found a nice setup for that one. Let's see now. Here you have some functions you can then put inside your control dict. And this one, yeah, he will then print out how much water volume do I have inside my my domain. It should be constant, at least initially, but remember you have an open top boundary condition, which is like the same we had in the 2D block mesh, no, the dam break case, When the water is slushing and then splashing upwards and go through the top, it's going to disappear. What's come back is going to be air. Hence, this volume is not going to be constant all the time. But initially, of course, all the water should be the same. So write this one out and especially check the initial values then for your different measures. That means you can only do, say, one time step, and then you should be safe, just to get a value for the initial water volume. So check that one out. Here also I have given you probes, the 8 different probe locations here punched in, so you don't have to worry about punching in all these numbers. So that should be okay, I think. And then when you simulate, yes, you will find these 8 pressure values, both for pressure and the pressure minus rho GH. Actually, you don't need that one, but that's another story. You need a total pressure. And then you'll find that one in the file, even Y plus if you want. So you should have been given here some tools. That should be nice. Yeah, here are the 3 different ways, at least in my view, how you can create this geometry. Your choice. Your choice. So in the end, I want a plot of your mesh. Now that one might be a little bit weird. I think I tried that one. Let's have a look here now. Parafoam. At least in my version. So let's see, here we have the feature edges and we organize it like that. Solid color. So there you have a side view of the entire domain. And yes, you can use, of course, stuff like surface with edges, but then since it's a 3D, you don't see anything. This is just the background mesh. And if you choose wireframe, you see too much. So not easy sort of to display what's the mesh around this one, for instance. So one way that should have worked would be sort of the following here. If I now choose a slice, and then I slice it here with the Y normal, then I just have one slice towards us, and then if we apply that one, and then I want to have a solid color and then surface with edges, then he does a very bad job. This is not correct. This should be only squares, and he has done something very weird here. You can see the idea here what's going on, but he doesn't show the mesh correctly, at least not in my version. You can try for yourself, but I mean, this one is actually quite terrible. So to show me the mesh, I would then actually suggest you do something like this. Surface with edges. And then we rotate him, and then we can zoom in here. Zoom, zoom, zoom. Where are my zoom? Here we are. Maybe something like that. Just show me the bottom, and then I want to see how you have handled the mesh around this box. Okay? That's good enough. And then I want the plot for all these probe stations with the pressure and the sensors. And how will they look? Well, they will then look something like something like this. 8 such figures. I want the pressure at the different probes as a function of time. And I want your curve with some error bars. Not for every single time step, that's not necessary. And also it's going to smear out the entire figure. But say at every second, I want a plus minus an error bar. So how do you do that? Well, if you look at the GCI description, typically then you have to evaluate for, say, one given time. And I would suggest time 2 seconds. Then the entire box is covered with water. So use that one as a, say, a monitor value for the different probe locations in your GCI study. And then you use that p-value. Remember the p-value. What was the p-value? That's, say, the most important thing in the entire study. Where are we? GCI procedure. Should be here somewhere. Here we have it. The third step in this GCI procedure, you evaluate the apparent order based on your monitor values for the 3 different meshes. And we know this one should be around 2, should be close to 2. We're using a second order accuracy in space, and then also you should use second order in time as well to reach 2 seconds fairly precise. So you just evaluate this one for the 8 different probes after 2 seconds, for instance. Then you may actually create one p average for all of these 8 curves and then use that value for the entire time history. We have to do something like that. So you don't have to evaluate this one for every probe, for every single time step. That will be a tremendous amount of work. So you can create one p average if you like, or you can have p 1 to 8 calculated after, say, 2 seconds, but you use that one for the entire time history to create the error bars. Remember, this one should reflect how good is your mesh. Hence, it should be time independent. That's the point. What else do I want? I want to have a list. I want to see these p-values. They should be tabulated. If you get some terrible p-values, and yeah, trust me, you're going to, then I won't kill you. Well, I'll kill you a little bit. But you should report it, and then you can discuss it later and say, okay, I know my meshes was a little bit too coarse here, but I mean, it's just an exercise for crying out loud. And also, I don't expect to have perfect results here. That's not the point. The point is, show me that you have understood the working procedure, how you can obtain it. So you can discuss it afterwards and say, okay, I know this version, this value is not, it's not good, but I use it anyway. That's fair. And yes, you upload the entire report, one single PDF file. As I say here, a couple of hints. I would suggest 2 seconds. I think the monitor value would then be more sensitive to the physics when the water has hit this little box and everything is covered with water. I think that's a good idea. You may try other times if you like, but at least that's my tip. Also, it's turbulent. Yes, it's turbulent. But I mean, this exercise here is not focusing on the turbulence itself. It's focusing on the free surface motion. So don't kill yourself by finding a mesh that even the coarsest mesh should then have a y plus value smaller than 300. close to the box, it should. I mean, around the box, that's where the interesting physics is happening. So that one should be resolved okay. But for the walls itself in the tank, don't worry about it. If you go above 300, that's okay. And yes, as I said, you can even play around with it when you have a result. Try to do one more simulation and switch off the turbulence. Run a laminar case and see if you can get any difference. I mean, is this, are the solutions, are they sensitive to the turbulence model at all? I'm not so sure, I haven't tried it. So there you have something to play with. I put the deadline next Friday, midnight. Is that okay? Yeah.
The other exercises we have like an exercise beforehand, which is contain like some relative information about the exercise we're going to have a report on. So do you have some similar exercises or tasks that have been done with this kind of multi-phase flow transient that we can compare and getting some information from?
Yeah, that would be the ideal world. Yeah. To give you first a play exercise with the free surface, this type of problem, and then give you this report exercise. But we don't have time, so I just give you one. Yeah. And it's very simple, it's very easy. I think you can survive that one. It shouldn't be too hard. But yes, I see your argument, and that was my intention as well. But we don't have enough weeks. Unless you want me to give lectures until late December, that's okay, I can do that. Just say the word. Yeah?
Is it possible for block mesh to refine the alpha water surface by itself, or do you need snappy expert for that?
You think this initial block here?
Yeah, if just for every time that block mesh could like refine the surface of the water.
Oh, now you're talking interface tracking, finding the correct position for the surface. It exists systems for that. I think I mentioned it when we had this quick overview of a multi-phase flow. Yes, it's possible, but not with this WOF system. So he will calculate 1 is water, 0 is air. 0.5, we have somewhere in between, inside one single cell, but you don't know exactly where. But he will actually track the surface quite nicely, actually. Although here, this initial state, you can see here, we have a small curve here. That shouldn't be there. It should be a square block. So that is due to the parafoam who interpolates from center to center. So it's a cosmetic thing, don't worry about it. But no, we don't have the correct interface tracking here, no. Would be fun, but no. Other questions? Okay, then this will be your task then for this week and next week as exercise. We are then going to continue using, focusing then on compressible flows. Yeah, just to make that certain, the model here for the air is incompressible, meaning we don't need the temperature. So this is pure incompressible flow. But is there no chalk here? Let's have a look at our basic equations. First we have the continuity equation. In general, I'll write it on the differential form here. You will have something like this, time derivative of the density, and then you will have the divergence of the density and the velocity vector equal to 0. There you have conservation of mass. Of course, no problem there. Then we have the momentum equations. And yeah, you can write them several ways, of course. This should be one way. You have the pressure gradient. Yeah, we have the gravity. And then finally, we have here the divergence. And here comes the total stress tensor, like that. Meaning, we haven't even said whether this is a Newtonian or a non-Newtonian fluid. Also, inside here, if it's a compressible flow, you will actually have a divergence of the velocity field, because in general, that's not going to be 0 anymore. Conservation of mass, don't call this conservation of momentum. It's not conserved. This is Newton's second law of motion. So the change of momentum equals mass times acceleration. So the momentum is not conserved. It's not a conservation. Let's just call it a momentum equation. That's okay. But then you have the energy equation. So one general form, you're using sort of the enthalpy here, small h. And then he will maybe look something like this. Total derivative then of the density. And we will have a nabla dot, and then Fourier's law here, K times the temperature gradient, and then here you will have a dissipation function. So that's the basic start for your Navier-Stokes. Of course, what we have done so far, incompressible. Incompressible. Then, of course, continuity is just the divergence of the velocity field. Momentum equation, well, it will simplify quite a lot, actually. Say the right-hand side is going to be the same. And here, well, we also have the pressure, gravity. But then here you will typically do for the following. You put the viscosity on the outside, and then you'll have the double derivative of the velocity field. So it simplifies a lot. And when it's incompressible, it's actually possible to make this equation here a little bit more simple. Then he will look something like this, rho, and then you have the heat capacity there, and then we're using temperature as a variable. Should then equal, and then you have the thermal conductivity K multiplied with nabla square T. Again, now all of a sudden this small k has been constant. Here it could be changing in space. Doesn't have to be constant. Same here. This viscosity, and that's a dangerous thing actually. This one doesn't have to be constant. In the general equation, no, not necessarily constant. But incompressible, things much easier. And then this dissipation function, big phi. Something like that. So these two versions, yes, they are cute, especially the one to the right. Here, you can draw a line here and say these two equations can be solved by itself. You don't need the temperature here, so you don't have to worry about the temperature equation at all, or the energy equation. So, I mean, they stand alone. After you have solved the velocity and the pressure here, then you can calculate the temperature if you want. So that's an option, it's possible, but you don't need it for anything. And so far we have skipped this one altogether. So they are totally decoupled. So here you'll have 4 unknowns in 3D. You have 3 velocity components and you have the pressure. That's it. Here is a different story. How many unknowns do you have? Well, you have 3 velocity components, you have the pressure, and you have the density. So that's 4. And then, depending on the version of this energy equation, we have several of them. Whether you use the enthalpy, the total energy, or you use the temperature, at least that's 1 more. So then we have 5 unknowns, but I only have 4 equations. I'm missing 1 equation. And yes, somewhere along the line here, you have to put up a state equation. You need a coupling between temperature, pressure, and density. Something must be said about that one. And typically what we will use then, ideal gas law for instance, pressure equals density, the constant R multiplied with something like that. So then it should be a closed system. Actually, you may even need more equations, like how is this parameter changing with the temperature? That's a physical thing, so here we may have to rely on experiments given some thermodynamical data somewhere. Can be dangerously changing. Even this one, thermal conductivity doesn't have to be constant, he can also change. So yeah, it can be a little bit messy. But sort of the big picture I think you have here. Any questions to this one? Okay, then we take a break.